Here in Chapter 11, we want to consider a process called linear regression. So far we had only considered one variable at a time that's measured on experimental units. We now want to consider bivariate data, or two variables at a time. So we'll have an independent variable and a dependent variable. And we want to look at the relationship here between those two variables. So in a designed experiment, we want to ask the question here, does it matter how much you study for a test? Just as an example here. So the deterministic model that would go with this relationship is an exact relationship between the variables. And that deterministic relationship is going to be the equation that relates the variables. So in a probabilistic model, you're going to have a deterministic component and then plus some random error. So we're going to denote the deterministic component as E of y, expected value of y, the dependent variable, and then we're going to have a random error on there. So the reason that we have this probabilistic model here is because it's not always the case that our data lies exactly on a line. If that is the case, then we have a deterministic relationship like this one, y equals 10x plus 50. So our y-intercept was 50, we rise 10 and run 1. That gives our line, and you can see that these points all lie on the line. So there's no error there. We know exactly what's going to happen for each x value. We can tell what the y value is. However, in real life, our data does not necessarily lie on a line. So what we want to do is find sort of the best estimating line that's going to go down through the middle of that data. So this is a picture of a probabilistic relationship, which is 10x plus 50, that same line, plus some random error. So, and that random error here is denoted by the vertical distances of those points off the line. So we're going to consider first order or straight line probabilistic models. They're going to look like the following. Y is beta 0 plus beta 1 times x plus epsilon, where y is your dependent or response variable, x is your independent or predictor variable. And so the expected value of y, which is our deterministic component, is beta 0 plus beta 1x. So this is just the equation of a line in mx plus b form. We're using beta 1 for m and beta 0 for b, and we've written them in reverse order. That's just the process that our book uses, or convention that our book uses. And then epsilon is going to be our random error component. So beta 0, again, is our y-intercept, and beta 1 is our slope. So let's look at an example here, a little bit of review. Let's determine beta 0 and beta 1, our slope and y-intercept, if y equals beta 0 plus beta 1x passes through the points 1, 2, and 3, negative 2. So remember what you do here is you label your two ordered pairs here, x1, y1 and x2, y2, and then remember that your slope is y2 minus y1 over x2 minus x1. So rise over run. So difference of those y's will be negative 2 minus 2. And then difference of the x's here, 3 minus 1. So that is negative 4 over 2, which is negative 2. So that is our beta 1 slope. And then we can plug into the slope-intercept equation for the line. So y equals mx plus b. If we're using our familiar algebra variables here, our slope is negative 2, so this is negative 2x plus b, where b is our beta 0. That's b, and that is m. And then we know that both of these points are on that line because the line passes through those points. So just plug in the x and y coordinates of one of the 2 points. So why don't we use 1, 2? So 2 is our y, has to equal negative 2x. So negative 2 times our x value is 1 plus b. So that's 2 is equal to negative 2 plus b. Bring that negative 2 over as a positive. Your b is going to equal 4. And then we plug that back in here. So the equation of our line is negative 2x plus 4. Or, again, your book likes to write that as 4 minus 2x. So that our beta 0, y-intercept is 4, and our beta 1, slope is negative 2. So that's just the equation of a line. So we've done that before. So looking ahead here, what we want to do is we want to find the probabilistic model, or the linear regression line. So what we're going to do is we're going to hypothesize what the deterministic part of the model looks like. So it looks like beta 0 plus beta 1x up here. And then we're going to use the sample data to estimate our unknown parameters of the model. So we're going to estimate the y-intercept and the slope from the sample data. Then we're going to specify the probability distribution of our random error term. That is our epsilon. And then we're going to estimate the standard deviation of that distribution. We do that in 11.3. Then we will statistically evaluate the usefulness of our model. So after we have our model, how good is it at predicting? And then after establishing that the model is useful, we're going to actually use it to predict and to estimate.